So bandwidth or max frequency, that's going to be half of our sampling frequency. So whatever your max frequency of interest is, you're going to need to sample at least 2 times that. And realistically, to avoid aliasing issues, we would suggest 2.5 times your max frequency of interest. And that's related to the Nyquist sampling criterion. But whatever your maximum frequency is of interest for your test, you need to sample twice that to avoid any issues with aliasing. So our max bandwidth is just half our sampling frequency. Spectral lines, when we talk about the total number of frequency points here on our spectrum graph, it's similar to block size. Block size, the number of points in the time domain. We're talking about now in the frequency domain though. So these spectral lines will represent that. And at each point, we actually have 2 values. That's because the fast Fourier transform, we get a complex number out of that. So it's has amplitude and phase, or we can represent it as the real part and imaginary part. And the spectrum line is going to be the block size divided by 2. Now, frequency resolution represented here is delta F stands for our frequency resolution. It's 1 over our frame size. And we can just think about it like this. If we had a bandwidth of 16 hertz and we had 8 spectral lines, then we're going to have a frequency resolution of 2 hertz, right? The distance between each one of these spectral lines would be 2 hertz. So as well, we could rewrite that equation and just say that delta F is the bandwidth divided by the number of spectral lines as well. And I really like this slide in particular because it kind of hopefully relates to you or conveys to you the relationship between all of these parameters we've been talking about, the bandwidth and the spectral lines, the sampling frequency and the block size. And one key point, this frame size, remember that's the amount of time we need for one FFT. If we want to have a really fine delta F, really small frequency resolution, then we need a lot of time, right? Just for the one average, we would need a lot of time. This needs to get large for this to get small, right? So that becomes an important point. Let's look at another demo though to highlight this idea of bandwidth and measurement time.
Great. And I thought I was maybe scaring you before, so I went in here and I changed the frequency of the sine wave I'm generating back down to 100 hertz. So we're back to a nice looking sine wave. Is that good for you, Charles?
Yeah, I'm happy.
Okay. And you can see up here, I got those settings you were talking about. I got sample frequency, I got spectral lines. And in fact, I think on your equation actually said bandwidth divided by spectral lines is your frequency resolution. And then there is your acquisition time. I'm going to go here back to Tools Options. I'm going to switch this back to bandwidth or max frequency. So instead of 1024, what this is saying is I can see 512 as my max frequency. I'm using 512 data points to digitize it. So like if I look at my frequency spectrum here, so I can say marker style cross here so that we can actually see those data points again. I'm going to zoom in. So I got 100 hertz, 4 volts. But what's kind of weird is if you look at this, you can see that the next data point over, well, this doesn't go right down here. If I put a cursor on and I right click on the cursor, say snap to data values, so it doesn't float in between. You can see at 100, I'm at 4 volts. Over here at 101, I am at 0 or something very close to 0. And then it's 0 from there out. There's really no data in between. It's just connecting the line. So what I have is, you can see I got a 1 hertz resolution, Charles. Does that make sense?
Yeah.
And if I look in the time domain, that 1 hertz resolution is 1 second long. So you can see here it goes up to 1 second. Now maybe I'd be like, oh, I'd like to see that little finer frequency resolution. So I would go up here to 512 and increase the number of spectral lines. So if I double that, now I got half a hertz of resolution. It's just these numbers divided. And now the time domain is 2 seconds. So I have to take a longer chunk of data in order to see this at a half hertz. So now as I move my cursor around, notice it's going a half a hertz at a time. Can you see that, Charles?
Yeah.
Yeah. Pretty nice, huh?
Yeah. Yeah. I like the point too that you pointed out that the lines, the way it draws when you're snapping to the data points, there's all your energy is at the 100 hertz. Nothing.
Yeah. So then I might say, gee, I want the finest frequency resolution possible. I could do something like this. Guess what happens? How long is my acquisition, Charles?
Really long time now. 2 minutes.
Yeah.
Plus.
I think when I first joined the company, I was working tech support one day, and the guy's like, my system seems to have locked up. I used to show the FFTs really quickly, but now it's like taking forever. It doesn't even come back. You know what he had done, Charles?
He had a really, really fine resolution.
Yeah, just cranking up the resolution, thinking, hey, this thing will still respond at the same rate. But yeah, these things, in some analyzers, other systems, it's true of all digital signal processing or data acquisition systems, that inverse relationship, you may not even see or know that the acquisition time had to be increased greatly in order to accommodate spectral resolution that you required. So you could get potentially strange behavior. Maybe I'll go for something that's a little less than 128 seconds. So now after 16 seconds, I should see the screen update. So and that's the time it takes in order to grab one chunk of time data to get a frequency resolution of 0.0625 hertz. So you can see there it came back. So yeah, that relationship dictates a lot. If you want this 0.06, if you have a Ferrari, right, Charles? Isn't it do like 0 to 60 in 4 seconds or something?
My Hot Wheels is variable. It depends on how fast I push it down the hallway there.
Oh, okay. So 16 seconds for a Ferrari, that FFT is going to be kind of you get a run up, you could get 4 run ups in or something.
Yeah, maybe 5.
Yeah. So I think you said something like, yeah, you got to be aware of these settings and set it appropriately for what you're trying to measure. If I got a 4-second run up, maybe I want 1 second FFT or a 1/4 second FFT. I'll give up a little frequency resolution to get a little more resolution over versus RPM or time or whatever.
Right.
So hopefully that gave people some appreciation for some of the practical aspects of bandwidth and spectral lines and the things that you were talking about there.
I appreciate it, Pete. That was very good. So some key points with regard to sampling frequency. If we're sampling in the time domain, we're working in the time domain, we understand the dynamics of our system, then we have to set no lower than 10 times the highest frequency of interest for us, and probably much higher than that, right? So we can capture the correct amplitude as well as we'll have a good waveform. Now, if we're working in the frequency domain, it's much less, right? Really only 2.5 times the highest frequency of interest with what we need to do. Once again, that golden equation is something to always remember. The shorter the FFT frame size, the smaller this cap T, then the coarser our frequency resolution is. But the longer this frame size is, then we're able to get a finer frequency resolution. But remember, that comes at a cost of, you have to think about how much time data you have, how quickly does the event that you're measuring happen. So you may need to give up some frequency resolution to be able to have an accurate measurement because you just don't have enough time data.